Hello everyone. Today I am going to present the paper The Era of 1-bit LLMs. All large language models are in 1.58 bits. On the first slide, we can see the main idea visually. On the left side, there are normal full precision weights, and on the right side, those weights are represented using only three values: -1, 0, and +1. This is the core idea of BitNet b1.58. The paper asks a very important question. Can we make large language model faster and cheaper while keeping almost the same performance? So in this presentation, I will explain the problem, the method, the results, and the limitations of this paper. On this slide, the paper introduces the main bottleneck of modern LLMs. Large language models are powerful, but they are also very expensive to run. They need a lot of GPU memory, high energy consumption, and they can have high latency during inference time. This becomes a problem where we want to deploy LLMs on smaller devices or when we want to serve many users at the same time. The goal here is called Pareto improvement. That means reducing the cost but not reducing the model's performance. On the graph, we can see that the target is to move toward the lower cost while keeping state-of-the-art performance. BitNet b1.58 is proposed as a solution to this cost and performance trade-off. Now we come to the main technical idea. In normal LLMs, weights are stored as 16-bit floating point values like FP16 or BF16. These weights can have many decimal values. But in BitNet b1.58, every weight is limited to only three possible values: -1, 0, and +1. This is where the model is called 1.58 bit, because representing three possible states requires about 1.58 bits in binary. The 0 value is very important. 0 allows the model to ignore unnecessary or irrelevant features, so it works like a kind of feature filtering. Another important point is that BitNet b1.58 is trained from scratch. It is not just a normal model compressed after training. This slide shows why BitNet b1.58 can be more efficient. In a normal FP16 model, computation requires many multiplication operations. For example, a weight like 0.2961 has to be multiplied with an input value. But in BitNet b1.58, the weights are only -1, 0, or +1. So instead of doing expensive multiplication, the model can often use simple addition or subtraction. For example, instead of calculating decimal multiplications, the operation can become something like x0 minus x1. This is much simpler for hardware to compute. So the main benefit is that BitNet reduces heavy floating point multiplication and replaces it with lightweight integer operations. Now this slide explains how the model actually converts weights into those three values. The paper uses a method called Absmean quantization. First, it takes the raw weight matrix. Then it calculates average absolute value of the weights. After that, it scales the matrix and rounds each weight into -1, 0, or +1. The model also replaces normal linear layers with bilinear layers, but it still keeps many familiar llama-style components. For example, it uses RMS norm, SUI glue, and rotary embeddings. This is important because it means BitNet b1.58 can fit more easily into the existing LLM ecosystem like Hugging Face or VLLM. This slide shows the experimental setup. To make the comparison fair, and the authors compare BitNet b1.58 with a reproduced FP16 llama-style baseline. Both models are trained under same conditions. They use the same training dataset and the same number of tokens and similar model sizes. The models are evaluated from 700 million parameters to 70 billion parameters. The authors test the model using zero-shot benchmark like ARC, Hellaswalk, Wino Grande, and Pickle. They also measure perplexity on dataset like Wikitext2 and C4. So the paper is not only checking speed and memory, it is also checking whether the model still performs well on language tasks. This is one of the most important result slides. At smaller sizes like 700 million and 1.3 billion parameters, BitNet b1.58 is close to the full precision baseline, but not always equal. But at around 3 billion parameters, BitNet b1.58 starts to match full precision performance. This is the key turning point. The model achieves similar perplexity and task performance, but with much lower memory and latency cost. This paper also shows that BitNet b1.58 with 3.9 billion parameters can perform better than the 3 billion Llama baseline while still being faster and more memory efficient. So the main message of this slide is BitNet b1.58 keeps the performance but reduces the cost. Now this slide shows the practical gains in speed and memory. As the model size increases, BitNet b1.58 becomes more and more efficient compared to normal Llama style models. At the 3 billion scale, it is about 2.71 times faster and uses around 3.55 times less GPU memory. At the 70 billion scale, the advantage becomes even larger. It reaches around 4.1 times faster latency, and the memory saving also increases significantly. This is very important for real-world deployment because in real systems, GPU memory and inference latency are major bottlenecks. So BitNet b1.58 can make large models easier to run, and it can also allow more users to be served with the same hardware. This slide focuses on energy efficiency. Because BitNet b1.58 uses mostly integer addition instead of FP16 multiplication, the arithmetic energy cost becomes much lower. According to the paper, for matrix multiplication on 7 nanometer chips, BitNet b1.58 can save around 71.4 times arithmetic operation energy. But we should be careful here. This does not mean entire system becomes exactly 71 times cheaper, because the full system also includes memory access, communication, and other overheads. Still, this result shows that the core computation becomes much more energy efficient. The paper also suggests a new scaling idea. A larger BitNet model may cost less to run than a smaller FP16 model. This slide summarizes why the paper is important. First, BitNet b1.58 changes the computation paradigm. It reduces expensive multiplication and replaces much of it with simple integer addition. Second, the comparison is fair because the authors use similar training settings, datasets tokens, and model sizes. Third, the design is compatible with Llama-style architectures, which makes it easier to connect with existing open source tools. And finally, the paper directly targets real bottlenecks in LLM deployment, memory bandwidth, latency throughput, and energy consumption. So this is not just about making a smaller model. It is about changing how future LLMs may be designed. Current limitations. The first limitation is training cost. The model must be trained from scratch. We cannot simply take an existing FP16 model and convert it directly into BitNet b1.58. The second limitation is hardware. To get the maximum benefit, we may need hardware specifically optimized for low bit or 1-bit LLMs. The third limitation is scale. The paper evaluates up to 70 billion parameters, but it is still not fully clear how this method behaves at extremely large scales. And finally, the paper mainly focuses on text language modeling. Its performance on vision language or multimodal tasks is still an open question. So BitNet b1.58 is a very promising direction, but it is not a complete solution for every type of AI model. To conclude, BitNet b1.58 shows that large language models may not always need full 16-bit precision, but using ternary weights -1, 0, and +1, the model can reduce memory latency, throughput cost, and energy consumption. This can open the door to several future possibilities. First, LLMs can run more efficiently on edge and mobile devices. Second, reduced memory usage can help support longer context length. Third, this can motivate a new generation of hardware design specifically for low-bit LLMs. So the main takeaway from this paper is simple. BitNet b1.58 is not just a compression method. It is a possible new direction for building efficient large language models. Thank you.